Hello, welcome to my presentation. My name is Shen. I'm a PhD student from University of Florida, Department of Mechanical and Aerospace Engineering. Today, my topic is on the extraction of large-scale coherent structures associated with broadband shock associated noise in supersonic jets. This presentation is brought to you by me, my colleague Shen Patel, and our advisor Stephen Miller. First, I want to acknowledge that this work is supported by the Office of Naval Research. Any opinions, findings, and conclusions or recommendations in the present work do not necessarily reflect the views of the Office of Naval Research. The presentation is arranged in following orders. We'll start our presentation with the background of the research. Next, the mathematical and numerical methods will be reviewed. After that, we will present the two off-design supersonic jet cases being used in the present work. Then, the decomposition results of the two jet cases will be shown. Finally, we'll summarize our work with conclusions and future work. Supersonic jet noise radiated from high-performance military aircraft have become a major health concern to military personnel working on the flight deck of an aircraft carrier. According to a report, the maximum noise level at the maintenance personnel position can reach up to 150 dB. The figure on the right-hand side shows the major noise components from an off-design supersonic jet. In the present work, we focus on the shock-associated noise, which dominates the far-field acoustic field in the sideline and upstream directions. The simulated jet flow field, as well as the proper orthogonal decomposition, are used to extract large-scale coherent structures responsible for the generation of BBSAN. The mathematical method used in the present work is based on the decomposition of Navier-Stokes equations, which was first proposed by Dr. Miller to predict the far-field noise generated by anisotropic turbulent mixing. The flow field variables are decomposed into time average components, the large-scale and fine-scale turbulent fluctuations, and the acoustic radiations. The decomposed Navier-Stokes equations are rearranged, and the acoustic pressure P prime can be solved by convolving the vector Green's function and its corresponding equivalent source terms. The source term for BBSAN was identified and validated by Shen, which is the dot product of the large-scale velocity fluctuations and the mean pressure gradient, where the mean pressure gradient represents the contributions from shock cell structures. This term needs to be extracted from the flow field to get the BBSAN spectrum. Since the BBSAN dominates the acoustic field in the sideline upstream directions, the governing equations can be simplified, and the acoustic pressure associated with BBSAN can be solved using the following equation. Proper orthogonal decomposition was introduced by Lumley to the field of fluid dynamics. The POD extracts modes from the flow field ranked by energy, where the energy is defined by a norm, which is a weighted inner product of flow field variables. In the present work, we follow the computational procedure by towing, and we use the inner product of the BBSAN source term as our energy norm, so that the energy norm is directly related to the BBSAN intensity. After decomposition, the flow field can be recovered using arbitrary number of POD modes. The numerical code used in the present work is called HiFiles, which was originally developed by Stanford University to demonstrate their newly developed scheme. The solver is a three-dimensional compressible Navier-Stokes solver, which is based on the energy-stable flux reconstruction scheme to achieve high order of accuracy on hybrid unstructured mesh. It can also be parallelized using MPI on distributed memory system. In the original solver, it also implemented several LES models. In the present work, we used the well model due to the presence of solid walls. To deal with numerical issues raised from the simulation of supersonic jet flows, the following new features are implemented in the solver. The first case is a hot unexpanded supersonic jet from a converging node SMC 000. The drawing of the node is shown on the left-hand side. The nodal parameter, the jet parameters, is shown in the table, which was used to reproduce a set point in the SHAR database from NASA. The far-field noise spectra are predicted using a Fox-Wheeling-Hawking acoustic solver and are compared with experimental data for validation. The figure on the right-hand side shows the noise spectrum at 100 degrees in the upstream direction. The BBSM lobes as well as the screech peaks are captured accurately. The second case is a cold overexpanded supersonic jet from biconic nozzle. The nozzle diagram is shown on the left-hand side. The nozzle is designed under the SATA program, and the operation condition shown in the table is chosen to match the experiment in a UF anechoic wind tunnel. The far-field noise spectrum at 100 degrees in the upstream direction is also shown on the right-hand side. The primary BBSM lobes are captured in terms of the peak frequencies and the lobe width, and the errors are within the acceptable range. The region which is expected to contain the BBSM source is used for the decomposition. The counterplot of the real part of the POD modes and the peak BBSM frequency observed from 90 degrees are presented here. The frequency is Strohmann number equals to 0.4. The eigenvalue spectrum on the right-hand side shows that the leading POD mode represents the screech mode. We can see from the left, the counterplot of the mode 1 shows strong energy on the first few oblique shock waves. The second mode shows strong coherency near the end of the potential core, so that it should represent the BBSAN mode. Again, the counterplot of the first two POD modes of the setup case are presented here. The frequency is the BBSM peak frequency observed from 90 degrees, which is Strohmann number equals to 1.0. In this case, there is no screech, so that we expect the first mode to represent the BBSM mode. You can see from the counterplot of the first mode on the left-hand side, the first mode shows strong coherency in the potential core and is quasi-periodic in the energy distribution, so that it can produce the constructive interference in the far field to generate the BBSM lobe. Therefore, we conclude that this mode is the BBSM mode. On the other hand, the suboptimal mode, which is mode 2, is chaotic and therefore is not efficient in generating BBSAN. The BBSAN intensity is calculated by substituting the individual POD modes into the equation for the BBSAN acoustic pressure shown previously. The BBSAN intensity calculated with suboptimal mode, which is the BBSAN mode, in the SHAR case as Strohmann number 0.4, and shows both downstream and upstream amplification centered at 35 degrees and 100 degrees, respectively. The radiation of BBSM in the downstream is possible when the turbulent convective velocity is high enough in the hot jet. However, the downstream BBSM is often masked by the dominant large-scale turbulent mixing noise in the downstream. On the other hand, the BBSM radiates from the optimal POD modes in the setup case at Strohmann number 1.0 and dominates around 95 degrees and radiates more than 7 times more acoustic power than the subsequent modes. And we also observed that the subsequent modes shows much less directional preference compared to the first mode. Finally, the BBSAN spectra at 90 degrees are reconstructed with different number of POD modes. We found that the key features of the BBSAN spectra, including the primary BBSAN lobes and the primary screech peak in the short case, are recovered with only the leading POD modes are used for the reconstruction. And therefore, we can conclude that the leading POD modes represents the large-scale coherent structures that generate the shock noise. To summarize our work, 2 off-design supersonic jets are simulated and validated. And the leading POD modes show strong spatial coherency and are efficient in BBSAN generation. The BBSAN spectra are recovered with only leading POD modes used for reconstruction. In the future, we propose to explore new decomposition methods that extract modes ranked by spatial coherence instead of energy used in the POD. And we also want to identify the source terms of large-scale turbulent mixing noise and extract large-scale coherent structures associated with this noise component. Thank you.